It's going to be Andreas Floer from Courant about the Arnold Conjecture. The Arnold Conjecture.
So this is the only Arnold Conjecture of why you stressed it at the well, the subject of the object of the Arnold Conjecture is our symplectic maps of symplectic manifolds. So maybe in particular, what we want to know about these maps are fixed points. So we don't. There might be some way of generalization towards more complex dynamic question of such maps. But what I will be concerned with today are just it's just a question of fixed points of such maps. So the easiest, simplest dynamic question that you can ask. Now, what is a symplectic manifold and what is a symplectic map? The simplest example of a symplectic manifold is a surface with a volume form. So omega is a volume form that is in this case a differential form of degree 2. And a symplectic map would then be a volume preserving map. So symplectic. And there have been several conjectures about fixed points of volume preserving map. First of all, of course, you see that for a torus, that I drew here as a standard surface, there are certainly volume preserving maps which do not have any fixed points. I can just take a rotation around any of these generators. But it turns out that if one adds a certain condition or a certain set of conditions, then one obtains maps which are always bound to have a certain number of fixed points. Let's first take the simpler case of a sphere. There has been a theorem that a sphere has non-zero order characteristic, and so certainly always any diffeomorphism of a sphere has to have one fixed point. But there is a theorem by I think his name is Nikishin, some Russian, that every volume preserving map of a sphere has to have two fixed points. In particular, it has to have as many fixed points as a function has critical points, and that's what we will use to, or that's the way we will generalize this theorem. In this case here, I always obtain at least three fixed points. In those cases where I fix the mean rotation around both of these generators to be zero. If the mean rotations are zero, I would make this a little bit more precise. Shortly. Mean rotation vanish. Now 3 is also the minimal number of critical points of a function. And if all critical points are non-degenerate, if all critical points are non-degenerate, then I even get get 4 critical points. So there are no critical points or fixed points. Then I even get 4 fixed points. Again, this is the number of critical points of a function which has only non-degenerate critical points of a Morse function. A similar...
So that's in the Arnold conjecture in this case?
No, this is the Arnold conjecture in this case. It has been... this is related to a theorem which is called the Birkhoff-Lewis fixed point theorem, and I don't want to go into this particular theorem, but maybe some people here know this. This has always been. This has been done sometimes in the early 70s, and there has been a paper proving the corresponding result for the torus. And as a matter of fact, for all surfaces, by the name of Eliashberg. But this proof was a lot of people did not understand the proof. Let's put it this way. And
but the proof was to the effect. To what effect?
That in this case, for the torus, there are 3 critical points. There are 3 fixed points. And 4 fixed points if they're non-degenerate, and in general for any surface, there are always as many fixed points as a function would have critical points, in the way that there are always where the coupling of this would be 3 fixed points. But if they're non-degenerate, then there are 2 times g plus 1. But I don't. Rather than stating this purely in the case of surfaces, I would like to generalize it to general symplectic maps and obtain also make clear what the generalization of this rather obscure statement is.
You don't have something like that in terms of higher genus? A constraint on...
You could probably rephrase it, but you will see what the correct statement is anyway for surface and for general matrix. One could think or one could say that the case of surfaces has been done by Nikoshin and by Eliashberg and forget about this whole complex of questions, but we would like to try to do generalizations of this for higher dimensions, and the question is, what is the correct generalization of the hypothesis? Well, there are 2 possibilities. Either one assumes the map to be volume preserving in any dimension, or one assumes that there is a 2 form which is preserved in any dimension. And what we are going to do is, it turns out that the correct way to generalize this form is to assume that there is always a 2 form which has properties similar to properties of a volume form, 2 dimensions. There exists. Now, what are these properties? The manifold I will call P. The properties of omega are first that it is closed. Of course, in 2-dimensional case, every 2 form is closed. But but in this case, this is a restriction. And the second is, well, here omega is a volume form, that means it never vanishes. And I wanted a similar statement here, but I have to not only to assume that it does not vanish, but that it is non-degenerate everywhere. And non-degenerate here means it is non-degenerate as a bilinear form on each tangent space. Now, if it is of such a, if it is bilinear, then that means in particular, well, this what I wrote here, it is the definition of a symplectic form. And every manifold that has such a form is called a symplectic manifold. And I now want to make more precise what this restriction on these maps is. First of all, I'm looking now at symplectic maps which preserve this form omega. It's yeah. The reason why it is always cohomological non-trivial is that this is equivalent to the nth cup, nth exterior polar of omega not to vanish. Where n is half of the dimension. So maybe I should state some consequence of this. One consequence is that the dimension of P is 2n, is even. There are no odd dimensional manifolds which have a non-degenerate form. Another consequence is that omega n vanishes nowhere as a volume form. So omega n is a volume form. And this in particular implies that the integral of omega n is not zero over P, and this is the same as the n cup product of omega with its the nth cup power of omega in cohomology. Now
that's for compact manifolds.
That's only for compact manifolds. Yeah. For non-compact manifolds, of course, omega can be exact. That is omega. So for compact manifolds in particular, we cannot have omega equal to the alpha. If P is compact. I should have said I assume that all my manifolds are compact here. Well, these are all consequences which don't really have anything to do with my field. So erasing now. But what is important is how do we characterize symplectic maps? Symplectic maps, which are defined as maps so that maps from P to P, so that f star of omega is equal to omega. They are certainly volume preserving with respect to this omega to the n, but they are a little bit more. I use this property here of non-degeneracy. It implies that for each run form on P, I have there exists exactly one vector field. If I call the one from alpha, then there exists exactly one vector field x alpha, so that omega of x alpha dot is this one. That's one way to rephrase non-degeneracy here. And it turns out that the vector field preserves the symplectic structure. That is, if we integrate the vector field, it preserves the symplectic structure exactly if this one form here is closed. So the symplectic maps are maps of the form, are maps generated by a vector field, maybe time-dependent vector field, which corresponds to closed forms here. And now I can tell you what is the generalization of this statement here. I'm looking at exactly all those maps which are generated by vector fields which don't only correspond to closed forms but also to exact forms. So I define, or for each function h from P to R, I define the Hamiltonian vector field xh as the unique vector field, so that omega of xh dot is the differential of this function. And that's the the dynamics created by this vector field, by integrating such a vector field, are called Hamiltonian mechanics. And we're looking now at the following set of diffeomorphisms of P. We find the set of exact deformations, just note by this symbol, as the set of all phi from x to x, the following property that there exists a family phi t. So there are P. Oh, P.
What is the subscript on D?
Yeah, it's E for exact. There's always it's a little bit more than just symplectic.
Exact.
Exact, yeah, it's called exact deformation.
Exact formation.
Exact deformation.
Exact deformation.
Or an exact diffeomorphism. But it's always called exact. Mm-hmm. Well, it's what I assume is that it is part of such a family. So there exists a family of diffeomorphism of P, so that phi 1 is phi and phi 0 is the identity, and so that d phi t over dt for each t is an Hamiltonian vector field. For some ht from P. Wow. So that's a fairly large class of maps that I'm admitting here. They can be generated by any time-dependent Hamiltonian. So what in a way what I'm admitting here is all maps that occur as a Hamiltonian in Hamiltonian dynamics. Arbitrary time-dependent Hamiltonians. So the theorem is, that one can estimate fixed points of such maps in DE by the topology of P. And now I only have 1/4 of the general theorem here. What I have to assume is that pi 2 of P vanishes, and I have to assume that, and I can only do the non-degenerate case. I have to assume that phi is such an exact deformation, so that all fixed points of phi are non-degenerate.
This doesn't include surface. No surfaces.
Most surfaces have this. Only the sphere. It excludes the sphere, but it doesn't exclude the others. So that all fixed points of phi are non-degenerate. Of course, non-degenerate here means that that the linearization of phi at x minus the identity has no kernel. So that this is an isomorphism. Or other that the linearization does not have an eigenvector equal to 1. Then, what I want to show is that one can estimate the number of such fixed points as one can estimate the number of non-degenerate critical points of a function. That is in particular then the number of fixed points is greater or equal to the sum of all Belly numbers. Equal to the sum over all Belly numbers. Now there is one more thing that restriction that I have to make. One would of course expect that one can take the sum of all Belly numbers for any coefficients. But I will have to restrict myself to the sum of all Belly numbers with respect to Z2 coefficients. That includes the sum of all Belly numbers with respect to R or Z coefficient. This number is always at least as big as that number. But I cannot do any Belly numbers with respect to ZP coefficient, where P is an odd prime number. But I mean, this theorem as it is now, I can prove.
Are you going to say why this is the equivalent of the no rotation condition, mean rotation of zero?
Yeah, it's okay. That's something that I should do. Take the torus and take its coloring. Then the precise statement of this no rotation would be that the integral of phi of x minus x, that the center of mass of the displacement here is 0. And one can show that
It's over some fundamental domain.
yeah, one would have to take it over fundamental domain. Or one can take the mean, but in any case, it's in any case that in any way that this makes sense, it has to vanish. So either mean or over 0, 1. And one can show that whenever this is the case, one can find such a vector field, such a family of Hamiltonians, and the other way around.
And in fact, you have to have varying Hamiltonians.
In general, yeah. now let's assume we do not have varying Hamiltonian. We have just a time-independent Hamiltonian. Then this theorem is trivial, because it is just if the Hamiltonian is not is time-independent, then the fixed points then for each critical point of the Hamiltonian are the fixed point of the whole family of diffeomorphisms. And that's one way how we can understand this theorem, this whole Arnold conjecture. It's just generalizing something that's obvious for time-independent Hamiltonians to time-dependent Hamiltonians.
Is that construction relating the two-dimensional case finding this family is empty? You're saying that's an exercise, or is that hard work to find H of if you start with something legit?
I would say it's an exercise as soon as you have you really occupy yourself a little bit with Hamiltonian vector fields. It isn't really very difficult. Okay, so I would like to say something about the proof of this theorem. And the main
This condition on the inertia is only on the end of the isotope. Only on
of course, if I would assume that this is non-degenerate everywhere, then again it would be trivial, because at a certain for small t, I certainly have this theorem. So this theorem is certainly true. Theorem is true for small perturbations of the identity. Now, it is then true if the deformation is C1 small, because then I can define this always by a time-independent Hamiltonian. That is because one has to do something about it, but one can relatively easily show it. Now, Einstein proved a couple of years ago that it's also true for C0 small perturbations. That is, if the Hamiltonian or if the Hamiltonian vector field is small in C0. No. The point is if the deformation itself is close to the identity in C0, then it's also true. If I assume that these maps were always transversal for all t, then of course I would have as many critical points as I had in the beginning, exactly as many critical points. So I cannot assume this. Now, this is actually going to become important for the proof. But first, in order to prove this theorem, I would like to convert this fixed point problem into a variation problem. So the principal idea is convert fixed points into critical points of some function. Now, what I would like to have is, of course, a function on the manifold P. But I'm not going to get this. Actually, I'm only be able to convert this into a fixed point problem, or into a variation problem in infinite dimensional manifold. So the manifold in which I'm doing a variation problem, I will call omega phi, and that is the manifold of all parts z from 0, 1 into P, so that z of 0 and z of 1 related in this way. So it's the set of all parts which connect a point in P with its image under this map. I can certainly always do this for any map, and for any map that is homotopic to the identity. This space here is diffeomorphic, or it's bijected to the space of closed loops, closed free loops in P. In order to make this a little bit more precise, I can see infinity here. I don't want to. I'm not going to use any Sobolev space or anything like that here. Now, what is the function Well, I can't really say what the function is. It's a little bit difficult to define. But I can say what the differential of the function is. And any such element z, the derivative of the function in direction of some xi, and xi would then be, well, this is z, then xi would be some vector field over this path. And I want to make the function so that this derivative is of this form. So that I just integrate z dot, the symplectic form evaluated at z dot and xi at each t, and just integrate this over t from 0 to 1.
Back you up for a second. You're starting with fixed points and you're trying to find another manifold and another function to sort of match up fixed points of the
fixed points to
critical
critical
manifold, critical points
Yeah.
of this other function.
I'm trying to find a variational formulation
So
for
the manifold is
this.
paths. Manifold you're looking at is a path.
Yeah.
Why is that the same as the free loop?
Oh,
Given a loop,
that's,
how do you make it into a path?
that's because phi is homotopy identity. For n diffeomorphism, which is a topic to the identity, I can show that this is basically the free loop space. It doesn't really matter that it is, but I can show you how you can define it. If I have a phi t and I have a closed loop.
Okay, I got it.
Okay.
Now, what was the function again? I was thinking one.
Yeah, I'm not going to tell you what the function
Okay,
is.
you're telling me d.
Yeah, and d of the function is this nice formula. Omega is a true form. It is at z of t. I can define this product here, and I can integrate the whole thing. Omega is not an exact form, but it's a closed form. Now it turns out that because omega is a closed form, this defines a nice function, at least locally. This is in the infinite dimensional sense. This is a closed form, and at least locally I can integrate it. I should maybe copy this formula here, that you can see it. So dA of z in direction of xi is omega of z dot xi order t integrate with respect to t from 0 to 1. Now, because omega is a closed form, one can show that this is locally well defined. Actually, I need also that this function is a symplectic map. So omega closed, and phi is symplectic. I don't even need that it's exact, but symplectic. That is a closed form. This is actually in infinite dimensional sense a closed form, and there exists an A at least locally. And then phi is exact, and since phi 2 of t is assumed to be 0, we find that A is 2. I'm not going to prove this. Now, how do we find solutions of why the fixed points are now critical points of this? If dA of z 0, then this can only be if the odd vanishes identically, because this form omega is non-general. If the odd is not zero at any point, I can always find a key so that omega of z dot and xi is non-zero, and then it's like the fundamental theorem for variation, fundamental lemma of variation over the. But it's in any case, z dot has to be a constant equal to 0, and that implies that z is just constant. Now that implies that phi of z of naught, which is of z, is equal to z. because of the boundary condition. So that's critical points are in one corresponding to fixed points. Of course, you can go the other way around. Get a critical point for each fixed point. Now the problem is solved. Now one can use variational methods to apply to this function. It turns out that some variations just don't apply, and this is the way you do variational theory here is the most important thing in this whole proof. And I think the most interesting is Kohlmann itself. What you do when you do variational theorem is you define a dynamics on this space, on this infinite-dimensional space, by the gradient obstruction, and then you somehow do. And the critical points of these new infinite-dimensional dynamics are, or the fixed point dynamics are the critical points of the world. So define a gradient. Define what is a gradient. So we need a gradient field, and therefore I need additional structure, something like a metric of three-dimensional space.
But this is like theory on
It is a little bit like most theory, but it's going to be, well, in some other way it's very different from it also. So it's formally it's like most theory. So I should one difference is that they don't really define a gradient flow, but something which only resembles the concept of gradient flow. So define well, what you do is.
But now you're trying to count the number of critical points.
Yeah. Now what I use here to define a gradient flow is not just a metric on this space. I use it on the manifold itself, and I use a particular type of metric. Define an almost complex structure on P, which is just a morphism of TP. That's the J square is my identity, and I will assume in addition that the bilinear form that you obtain in this way is omega of J dot dot is a metric. That is, it is positive and symmetric. You can always find such a thing. Then omega, J, and G together satisfy all the identities of a Kähler metric. Except the J is not integrable necessarily. So I'm looking at Oscom structure. And so I should say this is almost Kähler. Now there are all such J's, and as a matter of fact there are, and I have choice here, and I will use this choice to make my problem well defined. Now, the gradient of A, I will define as, well, I'll give it the name S of Z. Z is the element of omega. I will define this as J times Z dot. Now this is in a way the equation is only a vector field. If this Z, then Z dot is a vector field in whose direction the function is going to decrease. To increase. Let's plug it in here. Then we have omega of Z dot. No. So J Z dot, omega of Z dot, J Z dot, is just this metric of Z dot, and so it's got to be positive unless you have a constant loop. And
But it's vector of the loop. Is it the gradient?
this is a vector on the loop space, and it is in this sense gradient-like vector, which is all we need. All we need is that the function always increases in the gradient here, unless we have a critical point. It is in a very good sense the L2 weight in respect to this to the L2 metric on this space omega. It has a disadvantage. I would not like to define the gradient flow by the differential equation dz tau. I look at families, z tau, omega for tau, some real number, and the differential tau is dz tau of the tau is equal to the gradient, or usually one chooses sign condition here, that it's equal to the negative of the gradient. In this case, the function decreases under the gradient flow, which is the U condition. So I have to solve this equation and call such solutions of this equation trajectories of the gradient flow. Now it turns out that this is just a very well-known analytic equation. If I define the whole family of these sorts from R plus into P, so if I give it a new name called U, defined as Z tau of T, which is a map from R cross 0, 1 to P, then this equation is equivalent to the Cauchy-Riemann equation. That's du del U of T into 0. Because this is the partial derivative with respect to tau, this is the partial derivative with respect to t, and J is an orthogonal structure. So this is I should say that this is to be interpreted with respect to as a map from R cross 0, 1 as a subset of C, a complex plane, into the almost complex manifold P and J. So the trajectories of magnetic flow are holomorphic maps from the strip into P, which are for tau are elements of the space omega. That is, they satisfy a certain boundary condition.
From a big picture? Big picture?
Yeah.
Is that P down? What is that down there? Is that P or what is that? C.
P. That's a complex plane. Yeah.
Complex plane.
Yeah. Now, what I'm most interested in are the critical points. So I'm looking at, if you look at trajectories which we go from one critical point to some other critical point, then what I would get is a holomorphic map from the strip into P, which at each point carries this point of the boundary, so that at each point, this point of the boundary and this point of the boundary are related by phi. So that's the best picture that is known.
So,
I just you read this here.
so tau is going down and t is going horizontally here?
Yeah, in this case, t would go, tau would be this direction, and t would be this direction. Yeah. So it's a nice equation. There's only one thing wrong with it. It does not define a flow, because the initial value problem of this equation would be a Cauchy problem, but it's an elliptic equation, and I've told that the Cauchy problem for an elliptic equation doesn't make sense. In particular, it doesn't make sense for the Cauchy-Riemann equation, as one can just convince oneself by easy examples. So we do not have an existence of the for the initial value problem. For the initial value. But that's not so bad. What we do have,
the initial value problem here.
the initial value problem that is, it has given d naught in C infinity or in omega phi, that does not necessarily exist a trajectory. There does not no existence of no existence in general of such a v tau. Sorry about this. But that's not so bad. What we do have is certainly uniqueness. If we have one of them, then there is certainly only one trajectory. That's one thing that I won't need. But another thing that we do have existence, a good existence theory. A good existence theory for global solutions. For global solutions. And I should say here now of this equation. Equations are the same, but it's easier to see why they have a good global solution theory for the Cauchy-Riemann equation and for this. And the reason for that is that since the equation is elliptic, its linearization is Fredholm in a way, and we know that the solution space tends of such maps tends to be a finite-dimensional manifold, and that's what I'm going to use. So, given the lemma here that I will use is for any two critical points or two fixed points. The space of trajectories connecting these two fixed points, which I will define as the Morse cell between x and y, which is defined as the set of all u or u, so that du del bar u is 0, and u of tau is in omega phi for all tau, and the limit of u tau for tau going to plus minus infinity exists, and this is equal to x or y, depending on whether I go to plus infinity or minus infinity. That this space, the lemma is that this space is for generic J. If I might have to perturb the J a little bit, a finite-dimensional manifold. I don't know if it's empty or not, but I know that if it's not empty, then it's a nice finite-dimensional manifold. And that I know by taking the linearization of this equation and by proving that due to these boundary conditions, this is a Fredholm map between.
What is the u tau omega? Not sure what it is.
Yeah, u tau is supposed to be in omega of phi for each tau. So there are boundary conditions here and here, and there are boundary conditions here and here, which just fit together so nicely that I get a nice Fredholm linearization there. Now, why should that help us? It just it implies that the situation in my infinite dimensional space is just the same as in the finite dimensional space, as at least if I concentrate myself, if I restrict my attention to global trajectories between critical points. So let's recall what the situation is on a finite dimensional manifold. Finite dimensional manifold, that means a torus. If I have a Morse function on a finite dimensional manifold, which in this case would have usually four critical points, then I can always define these spaces of trajectories connecting x and y in basically the same way, just taking some metric g and taking the gradient of f with respect to g and taking the corresponding flow. And I find out that this space is also is finite dimensional manifold for generic G in this case. Actually, for an open dense set of G's. And in this case, the gradient flow is called a Morse-Smale flow. It is a Smale flow. Also, the dimension of this space can be identified by looking at the Morse index. It's just the difference between the Morse indices of x and y. So this mu is the Morse index. And so this is the first statement. This is the same statement that we have there. And I'm going to produce here another couple of statements which can also be generalized to this situation. The third thing is that if I look at critical point pairs, let's first take an example. This is the maximum here. If f is just the height function, this is a critical point of Morse index 1. So we expect to have a one-dimensional space of trajectories between this point and this point. And as a matter of fact, we will usually have two trajectories. These are 2 points of index difference 0. Now, if we had trajectories between these, one trajectory between these 2 points at all, then since the trajectory equation is invariant with respect to translations in tau, you would have a whole one-dimensional family of them. So the result is that we cannot have any trajectory between these 2 critical points. And usually one is tempted to assume that there is such a trajectory, but it's unstable for generic G's. They would vanish and would become trajectories between this point and this minimum. So if we look at all the one-dimensional trajectory spaces, then the picture would look like this. We have one-dimensional trajectory spaces here and here, and well, I guess I should watch out that they don't cross. We have one-dimensional trajectories here. Now the observation is that I can recover the Morse inequalities just by looking at these one-dimensional trajectories. And the way I do it is I define by C star the free abelian group over all the critical points. And then I define an operator B from C star to C star, or delta, and define the following way. If I take any critical point x, then I look at all trajectories which go to critical points of the next higher index. And I just count them. So it's the sum, delta of x is the sum of all critical points y for mu of y is equal to mu of x plus 1. And I just the number that I put in here, which I call x delta y, which is the matrix element, is just the number of trajectories. And to be more exact, of course, there are infinitely many trajectories. I have to quotient out the translations in tau. So I'm just looking at geometrically different trajectories here. Now this is an old observation. That one can define this delta, and it's also kind of implicitly known that this delta satisfies delta equals 0, and that the cohomology delta of C star with respect to this delta just recovers the cohomology of the manifold itself. This is one way to define to prove the Morse inequalities. So all we have to do now is carry over all these lemmas. One we already have, but all these 2 or 3, this property and this property to our interdimensional case. Now I won't be able to go into any details of this, but this pretty much describes the proof of this, of the Arnold conjecture.
And the Arnold conjecture, what exactly?
Now, the Arnold conjecture is the theorem that I proved here. Plus, of course, the Arnold conjecture should not have the restriction that pi2 is equal to 0. Mm-hmm. The conjecture is that it does hold in the general case. Also, there is an additional conjecture in the case where the fixed points are not non-degenerate. And then one would still have an estimate like similar as for critical points for a manifold, just by using the coupling or something like that. In this case, one maybe it's not quite clear why this implies the statement of the theorem. But obviously, if I prove all these things here for my gradient flow, then I know that the cohomology, that the critical points of a abelian group over the critical points serves a model for the cohomology of P. And of course, I have to have these generators of this group as of this group, and that is the estimate for the critical point.
How can you show this has one critical point?
At
least one.
If that is true, it certainly does. Now, and I think how is it? I prove all these by standard Fredholm theory methods, and in order to prove this, which is of course the hardest part, I just deform the whole thing from the phi that I have within omega into identity. So I use the fact that I actually have a family of deformations. And then I show that this cohomology doesn't change during this deformation. And then I show, then I use, then I just look at some simple case for which is close to identity. And that's the only case where I can actually prove the existence of such trajectories. And it turns out that if I have a Hamiltonian, and I look at the phi which is created by this Hamiltonian, generated by this Hamiltonian for small t, then the trajectories just correspond. One correspond to the trajectories of the gradient flow of the Hamiltonian itself. That one can do fairly directly.
Right. Well, questions?
There's one thing that I should say. That this whole method of using this gradient flow just depends on the fact that the trajectory equation is Fredholm, I don't really need that I have a symplectic map here. I just need the fact that I have a map so that J that anything that I don't have the situation where I map a plane on its J, on its orthogonal with respect to J. So there is a lot of more freedom, and I just don't know how what is the right thing to assume to get fixed point results. It might be a little bit more general. Okay, that's
Thank you.